Thank you. Today I want to tell you about positroid varieties, like the previous talk. But maybe what I should say is that now the positroid varieties we're considering are closed ones. So all of this is work with my academic sibling, Pranav Gondla, and then Josephine Levinka, who's also at Berkeley. So I want to begin by talking about two varieties that I like. So the first is toric varieties, and the second is Grassmannians. And I'm not going to define either of them because everything that I want to say will be on the slides. So the first is, if you take a toric variety, it's stratified by these torus orbit closures. And then also, your toric variety corresponds to a lattice polytope, P. Moreover, when I say corresponds, what I really mean is that faces of this polytope correspond to the torus orbit closures. And then it's also interesting because there's a connection between Ehrhart theory and the toric variety. Namely, the Ehrhart polynomial of a face equals the Hilbert polynomial of the torus orbit closure. And then finally, and this is maybe a little bit less familiar, if you take a toric variety, and as Kai Tao talked about, you look at this non-negative part, you can do it very naively. It lives inside projective space, so you can just look at the projective coordinates that are non-negative. And then this has a regular CW complex structure given by the intersections of these torus orbit closures with your non-negative. And moreover, this is homeomorphic in a natural way to P, your polytope, in the sense that it sends these torus orbit closures to faces of the polytope. So that's toric varieties. Now I want to talk about Grassmannians. So Grassmannians are stratified by positroid varieties. And these positroid varieties are due to Knudsen, Lamb, and Spire. They were talked about earlier. And the reason I want to talk about positroid varieties and not Schubert varieties is because positroid varieties play a little bit nicer, especially with that last one. So the totally non-negative Grassmannian has a regular CW complex structure given by these positroids. So this is a theorem of Galatian, Karp, and Lamb, and it's very hard. Okay, and so then the point of this talk is maybe to address like the other facts that I selectively picked up. So first of all, we're going to address, okay, toric varieties correspond to a lattice polytope P, but it's very easy if you think naively, maybe you think, okay, I'm going to have a polytope where for every face I get a positroid. But then if you consider GR24, there are, I think, like 4 positroid divisors. And so then you need a 4-dimensional polytope with 4 facets, which just isn't going to happen. So to the Grassmannian, we still associate a polytope. And this polytope is PKN, I'll call it. This is the Gelfand-Setlin polytope associated to a fundamental weight, but you could also think of it as a certain order polytope. And okay, instead of associating a face to each positroid, now we're going to associate a polyhedral subcomplex. So we're going to associate a union of faces. And so we've established like these two analogs, although in a very silly way so far. Okay, and then we prove some theorems about these polyhedral complexes. So first of all, there is the Ehrhart theory connection. The Ehrhart polynomial of this polyhedral complex equals the Hilbert polynomial of the positroid variety. Second, well, okay, if you associated a polytope, then automatically you'd have that polytope is homeomorphic to a closed ball. If you have a polyhedral complex, it's not necessarily true, but the polyhedral complexes we're associating are still homeomorphic to closed balls. Also, the boundary of a complex associated to a positroid is the union of a bunch of other positroids. Each point is in exactly one interior of these fence complexes. And so they give this polytope the structure of a regular CW complex, homeomorphic to Gurk non-negative. And so this is kind of analogs of these toric varieties. And okay, so a lot of the stuff I said on the previous slide is basically the artifact of the fact that we can actually show that there's a flat degeneration of the positroid to the reduced union of toric varieties corresponding to this complex. And so this was done for the Grassmannian by Sturmfels, and then maybe for Schubert's and like the flat variety in general by Gonchal Lakshmabai. Yeah, and so I wanted to mention, but before that, I wanted to say the stratification theorem, like the regular CW complex theorem, that's not going to just follow from the toric degeneration. I think that's more special to our case. Yeah, so I wanted to mention a couple of, fun identities. So, okay, if you plug in a negative number into the Hilbert function of a positroid, you could ask, is there a combinatorial interpretation? And so this gives one. And then the other thing, which I think can also be proved maybe more geometrically, is this kind of amusing identity about the Hilbert functions of positroids. So this is at least a statement that doesn't involve our polyhedral complexes. And then finally, I wanted to mention two more corollaries. So Almusa, Gao, and Huang give this recursive formula for characters of these cyclic de Mazur modules. So what a cyclic de Mazur module is it's just like, basically it's like the global sections. Like if you have your positroid variety, you just take global sections of some twist of a line bundle. And so, similar to like these it generalizes these de Mazur modules and then, these SLN representations. And so our results give a kind of polyhedral lattice point counting proof of this character formula. And then the second thing is we also can characterize in certain cases when positroids are arithmetically Gorenstein. So this was previously done for maybe at least Schubert varieties by Schubert varieties and Richardson varieties in the Grassmannian by Darian, and we can do it for some positroids. Thank you.
Any questions?
How do you look at a polyhedral complex and say that's arithmetically Gorenstein?
Oh, so all the ones we can do are polytopes. So they're order polytopes, and in particular, the order polytope. We use this result of Stanley, which talks about like the Hilbert series, relates the Hilbert series to arithmetically Gorenstein. And then for the order polytope, there's like a nice description of when that Hilbert series satisfies the arithmetic Gorenstein property in terms of the post.
We have time for one more question. There is. That's that camera again.